Welcome to our Future Flight webinar, first of the new academic year. I think in the chat box, you've got functionality to ask questions. We've had none pre-submitted, so please do, as we go through, think of some questions and put them forward. What we're going to cover today is a quick welcome from me, and to make everyone aware that on the call we do have teachers who have worked with us before. We've got students on the call and some who are new to it. So please, if you've got some words of advice about running the project, you want to contribute to the chat, please do so. And apologies if I'm going over some stuff that you already know. So I'll pass you over in a minute to our two engineers from ZeroAvia, and they'll talk about the role of ZeroAvia and the project, because this project was co-developed with them. In fact, they took the lead on it. And there will be a quick demonstration of the software, the OpenVSP software. Then I'll go through very quickly the phases of the project so you understand what the next steps are, as well as share some of last year's submissions so the students and teachers can be aware of the type of thing that might be coming out at the end of the year's project. There is some updates from last year as well. So if you're sitting there thinking, well, we did this last year, there are some nuances, some changes. So you might even want to get some students from last year to have another go, because I think we probably made it a little bit more challenging for them. And then, as I said at the end, questions at the end, but if there is something relevant as we go through, please do submit those questions. So with no further ado, I'm now going to hand you over to Pablo and Harrison from ZeroAvia. So I'll just stop sharing my screen now and pass you over.
Thank you very much, Mike, and I'm going to share my slides that we have. First of all, we're very excited to partner with IRIS on the second iteration of the Future Flight Challenge project. And I think this is a very good project to be able to contribute and partner with, especially with a company like ZeroAvia. First of all, a little bit about myself. I joined the company 2 years ago. Before that, I studied aeronautical engineering, and have been 2 years at the company. I'll let Harrison introduce himself now.
Hi there, I'm Harrison. I'm a mechanical design engineer at ZeroAvia. I've been at the company to a similar timeline as Pablo. Before that, I graduated from Nottingham University with a bachelor's in mechanical engineering, and since then I've been working at ZeroAvia to help decarbonize future flight, essentially.
Fantastic. Thank you very much, Harrison. So essentially, why is this project so important? What's the mission of ZeroAvia? Well, if we look at the emissions that aviation produces as a whole, it currently produces or accounts for 5 to 10% of the whole CO2 emissions. Now, the issue here is, as we are decarbonizing industries such as the automotive industry with electric vehicles, and of course we're creating energy with renewable sources, aviation will just grow in its percentage. And the fact is it can reach to 25 to 50% by 2050. This means that half of the CO2 emissions would be due to aviation. Of course, this would cause governments to rethink whether we could even fly for these purposes. So what we are trying here to achieve at ZeroAvia is a path to net zero. So what net zero is, of course, is no CO2 emissions from a life cycle perspective. But ZeroAvia has a plan further, which is to reduce CO2 emissions completely. And how we plan to do that? Well, there's a few ways that we have viewed, and one of those is hydrogen electric aircraft. Now, we'll explain a little bit about that powertrain, but essentially there's three main branches of powertrains that could decarbonize aviation. The first branch includes sustainable aviation fuels. Now, these are, of course, the easiest way to start decarbonizing aviation, because you essentially create fuels in a sustainable or renewable way. and you can use the same aircraft you're using today. And this is all right, but it has problems of scaling. Imagine you had to have all current aircraft flying on these fuels. You would need a lot of investment and production facilities for this type of fuels. Now, of course, the second branch is to electrify aircraft. And by this, there's a few variations of it. There's battery electric and there's hybrid electric. Hybrid electric, of course, meaning you do a combination of both combustion and electricity. Now, the problem with these, of course, is the batteries, and they're very heavy and aircraft have to be light. So what we feel is one of the most promising technologies is using hydrogen and actually using it with a fuel cell that produces electricity. So we're going to explain a little bit about how this works, from actually having a hydrogen molecule that you can see on the left-hand side, and that goes into a fuel cell system that converts the hydrogen with the air through a chemical reaction into electricity plus water. And of course, there's a byproduct of heat. Now, then this we distribute it through the powertrain, and what you'll see in this project is that we've created a framework for you to be able to design an aircraft that uses this powertrain. And of course, we're mainly focusing on how we're going to place the hydrogen tanks, which are liquid hydrogen, of course. I'll let now Harrison explain a little bit about what flight testing we've been achieving, and of course about our future plans that we have. So, Harrison.
There you go. Sorry, I was on mute.
No problem.
Yeah, previously, I believe it was 2020, wasn't it, Pablo? Was the first
That's
flight
right.
of the oh no, sorry, it was last year, 2022. Essentially we made our first flight with our 20-seater Dornier 228. So you can see it there on Pablo's slide, and essentially it features one side which is hydrogen electric. So inside the aircraft we have a hydrogen tank, we have fuel cells, all the other associated infrastructure that we need, such as inverters, and then the engine or the propeller that you can see there features electric motors. And those motors spin the propeller and propel the aircraft forward using essentially the energy from the hydrogen. Going forward, we have a number of different test flights planned. So currently we're working on an A to B flight. So essentially that is, and that's for this specific aircraft. So that is going from one point to another. So that's currently what we're working on with this. You might ask, well, have you just been flying in circles this whole time? What you've got to remember with this is we are regulated by the Civil Aviation Authority. So there's stringent rules around that, which makes it quite difficult. Hence why now we're only flying an A to B route. But going forward, we are looking at launching our sort of commercial aircraft next year. So that will feature our own developed motor and our own developed fuel cells as well. And there's lots of different areas that we're looking at. The company is also looking at infrastructure as well, because we need to provide infrastructure for these new fleet of aircraft, and we need that infrastructure on our site as well. So that's everything from producing the hydrogen to storing the hydrogen to fueling the planes that we have, etc. So yeah.
Fantastic. Thank you very much, Harrison. So before we go on to the exciting part of showing you the software that you'll be using, we wanted to give you a bit of background as well about how we've developed our spreadsheet that you will be using. So we, of course, in our company, we have a whole team that's dedicated to doing design and simulations. Now, when you start off with any design, you really want quick methods that can assess what an aircraft will look like as a whole. And for this, we use spreadsheets in our company. So this spreadsheet has been developed from methods that we use in engineering. So it's, I think, a great opportunity to be able to see. Of course, the spreadsheet contains a README page, which has interesting information, which is, I think, a must read because it gives you a good understanding of how the spreadsheet works. Then has a baseline with some of the calculations. For those of you who are interested, you can go and look into how we've built the aircraft design that you will be essentially taking forwards and investigating and researching about. Finally, we've also helped with some of our retrofitting calculations. So of course, we're implementing a hydrogen-powered aircraft, but what we're doing is we're constraining the problem to how are we going to fit these tanks, whereabouts in the fuselage are we going to fit? And so the information on how the powertrain and the electric motor with the fuel cells, how that has been designed can be found in this tab. And then next is, of course, the thing you'll be using the most, which is the iterations spreadsheet. Now in engineering, it's very important to iterate. You start off with one design. You might want to try it and analyze it with OpenVSP and then move forwards. So of course, the way we work with that is we try and come up with a concept. For example, we'll choose no tanks on top of the fuselage, and as you can see that picture there, it is animated so you can see, and we'll put 2 tanks inside the fuselage. With those 2 tanks, we will have to, of course, check the zero lift drag, which in this case shouldn't be impacted from the model because we're not putting anything outside of the aircraft. So we can input that there, and then of course we can check what our range is. Now, of course, in here we can almost get to Dundee. So this is a brief overview. Of course, whatever is grayed out is for you to, of course, look at, but maybe not touch, because is where we do some of the calculations for volumes and let's say the back end calculations of the spreadsheet. And with this, I'm going to leave to Harrison so that he can show the OpenVSP program in action. Thank you, Harrison.
Hey all, just share my screen now. Great. So can you see that, Pablo?
Yep.
Great. Yeah. So for some of you that may have done this project before, this will just will be me showing you the software itself, and for those that are new, it will give you a bit of a taste of the software itself. So yeah, OpenVSP is like a parametric modeling tool. So it has been used previously within aerospace to do quick concepts. And the way in which you would use it in the project is to essentially assess what impact tank placement has on the performance of your aircraft from a drag point of view. So the aircraft we've got here is the Dornier 228, which is the aircraft that we have flown, right? And is hydrogen electric. Now you'll be developing a Boeing 737, but we're going to use this aircraft for demonstration. Now, let me just do this. So there's a couple of different views. You can use wire, but the one that you'll probably want to use is a shaded one. It's a bit more user friendly, right? So you have your aircraft, and then essentially what you, in a nutshell, you're inserting different types of tank. So there are 3 different tank types. There's exterior tanks, exterior fuselage tanks, sorry, fuselage tanks and wing tanks. Now, when I put them into this model, you'll see that the wing tank, the fuselage tank doesn't fit in, and that is because this has been developed for the 737 and not for this aircraft. So for this demonstration, we're going to use one of the wing tanks. Great. So you can see there's a wing tank here, and you can then place it and put it into the position in which you want and assess what aerodynamic impact it has. So what I'm going to do is just quickly run through that. And what we want to do is actually we want to hide the nacelle and the prop because they will affect, let me no show it, there we go. They will affect our drag calculations, whereas in reality, the prop actually is what gives us our thrust. So we use parasite drag or parasitic drag. And in the setup for it, you'll see there is a video and there's also a PDF which will tell you what sort of equations we're using and what atmospheric conditions we're using, etc. And that sort of stuff, and where you want your reference to be. So, for example, the wing. If you then calculate, here you go. So it calculates CD0 or your drag coefficient, and it will break it down for you as well. So it will tell you which part is generating what essentially. So CD, And this is quite a useful column here, is your percentage of total. So that will tell you what is causing the most amount of drag. So you can see our wing is actually causing the most amount of drag. And we can then use that and put it into our Excel spreadsheet, and that will tell us the range. We can then insert a wing tank, for example. So I'll put my wing tank here, and you can move it as well. Sometimes you've got to play around with it a little bit to get it into the right spots. So essentially a wing tank would be somewhere in that location. And what you want to check as well is that it's touching. Yeah. So that looks good enough to me. In reality, that would be on both sides. So you can, if I can remember where it is, you can actually mirror the, you have to bear with me, it's been a long time since I've been using this software. Symmetry, here we go. So excellent. There we go, right. So now we've got tanks on both sides, and now we can rerun our drag calculation. I actually didn't make a note of what it was before, but essentially what we'd expect is that so here it is down here. We'd expect that this value is has increased. So we've got 0.0, so let's say 24 here. If I was then to hide this and rerun it. Yep, so you see, then we've got 0.018. So essentially that shows that adding 2 wing tanks increases the drag coefficient of our aircraft, which makes sense. So that's why then there's a way up. Okay, maybe I want to put a tank inside the aircraft, but the problem is then you have less space for passengers, which then means that your cost per passenger mile increases. And essentially what we want to do is get a maximum range, and whilst also minimizing our cost per passenger mile. And that is one of the outputs that you will see from the Excel spreadsheet. Yeah, so that's OpenVSP in a nutshell. There's a lot more complicated and complex things you can do with it, but essentially that's how you can start using it. And there's a series of tutorials as well on how to use it. Don't know if there's any questions on the software. Anything I've missed, Pablo?
No, I think that summarized it very well. And of course, the last point, which is, of course, we want to try and make an aircraft that is as efficient as possible. We're measuring that with what Harrison mentioned is a cost per passenger seat mile. So we're using the cost of the hydrogen that we use over a certain range. So yeah, as Harrison mentioned, again, if you have any questions, please put them in the chat. If it's also about ZeroAvia, about our work, what we do in our daily lives, we would be more than happy to reply to that as well. But over to you, back to you, Mike, so you can continue with the presentation. Thank you.
Thank you. I'll just put the, there we go. So thanks, gentlemen. A couple of key things. That is a very, very quick overview. There are tutorials in the phase 2 showing you how to actually pull in the models, download the software, and develop all that Dornier model, and then how to work to get the actual 737 model and do the same process. Within phase 1, most of you are at phase 1 now because you're submitting names and such like, and please do the survey, the advanced survey. What we have then is the phase 2. Now, when you look at the phase 2, there are some worksheets which are mathematically based. Can I be clear? You do not need to be able to do and complete the maths. So we do want to make it so that people couldn't move forward to the design phase because they struggle with the mathematical side. However, if any of you are looking further towards the aeronautical industry, or certainly if you're post-16, you should be able to go through the maths. One of them is actually completing answers and filling it in. And if you want to submit that to me, I can go through that and give you some feedback. Another one is some quite complicated fluid maths. And for that, there's not so much questions. It's just being able to follow the flow through. There's also lots of links to videos about aerodynamics. It's important in a way that you do go through some of that process so that you understand the context of what you're working with when it comes to your aircraft design. And for the answers to some of these, or the data that you require, mathematical data, can be found within the Excel spreadsheet that Pablo illustrated one of the tabs of retrofit. So this is some of the numbers you require to go into that. If you're doing year 10, year 11, you should be able to follow this through. And it's interesting actually from your physics learning as well. It's useful to be able to follow these things through. So phase 3 is where you actually start addressing the challenge. And as we see, there's a spreadsheet that Pablo illustrated, and that's where you work from, because you notice down here there's a retrofit design 1 iteration. This is where you would put your tanks in. You would then build your model in OpenVSP, and then you would actually then do your calculation of your drag coefficient. You would put that in there, and that will give you an answer. There's also a spreadsheet here for you to go through the process step by step. So this is, you have your baseline model, and then this is a model with the wing tanks, and you can see that this is my answer for my range and my percentage change to the original aircraft. Because what we want you to do is learn, one of the key things about engineering is you don't do it first time and get it right. What you tend to do is do it once, have a look. If that's not quite where you want it to be, you go over and you do it again. So it's called an iterative process. So we go back to here, you'll see you have retrofit design 1, iteration 1. So you would do that, and then the next time you would copy that tab and do design 2. And in design 2, you would change something about this. And gradually you will build up a list here of all the different permutations until you get to a point where you've got this chasm. This is what we're interested in, pence per mile. Now, there is a flow sheet in phase 3 to take you through the various steps, so you can actually work your way down through and then go back around the loop. Now, for this year, we've put in a couple of tweaks for changes from last year. The first one is a base design. So much like Harrison was saying, this is the base design now for your 737. So when you've got your model, you have to hide the nacelles and all the other bits and pieces. So you've got this design here, this very clean skin of a 737. This here are the figures. So these are the parameters that you need to make sure you've selected. You run a calculation, and that will give you your baseline CD. So that's without anything added to it. And we brought that in because last year, 1 or 2 students were starting with designs with maybe some nacelles left on and such like. So it didn't sort of give it a level playing field. So that's why we've introduced this base design. Last year as well, the hydrogen tanks were all the same shape, whether they were external or internal. This year, we put some new models. So if any of you ran the project last year, please ensure that you do download the new models. They're all available in the phase 3. On the project page on the right-hand side, near the bottom below library. That's where all the models are and the software is. So make sure you use the newer versions, because I know some of you might have downloaded from last year and the students will just pick up on those. Please make sure you use the new ones. We've also added in a couple of tutorials, one for being able to put a background to this. So when you've got your plane design, you, as I said in my email, you can end up putting it on the playground of your school if need be. But you can put a design to the back of it, as well as how to download it into files. So if you have the ability to 3D print, you can. Now, this comes into where you can go with this project. Now, some previous, as we'll see, previous students have submitted posters and designs. So if you go into the library, you'll find this booklet, and in there are all the designs that we submitted before. So this is from Joseph Wright Centre. So you can see they put along external fuel tanks on there. And we've got another one here from Mill Hill. They've got some internal ones. you can see how these designs are all different, and that's great, and that's what we want. But now we've given you the option for 3D printing. You might decide to 3D print your design and build a wind tunnel. There's plenty of little models, and look at the actual airflow through it, and maybe that could be part of your research, your investigation. Also, it is about the design of the plane, but as Harrison said, ZeroAvia are looking at infrastructure rather than just having the design. You might think we're going to look at infrastructure design for these airports, because we could end up building these more around the country, and we need to look at that infrastructure. What does it actually take? So you can see all the different ways you can actually approach this problem. But fundamentally, one of the key things I would say is watch the videos, read the instructions, and look at the software, because getting to grips with that is important. Now, I think I'm going to stop sharing now so I can see if there's any questions. Any questions from anyone at all? Any questions for the engineers or about the project? Just looking down. So, as always, if you do think of something afterwards, or you watch this video through and you're thinking, I wish I'd asked, just drop us an email, and I can then ask. If it's something I can't answer, I can ask Pablo and Harrison to actually help me with an answer. Or we might have a question. There we go. 3D printing, creating the wind tunnel are useful sites of visit to have a guidance of how this should look. I'm not sure how many of you seen. I sent out an email, but I know we've got someone joined us who hasn't signed up to Irish yet, but is interested. I can send you an email with some links, but then it's over to the students. And this is a very important thing, actually. Our projects are around students doing this and teachers facilitating, of course, for the health and safety. But it's really up to the students to go away, look at designs of things, and then say, is this practical? Is this not practical? So I've looked at some. You've got a small 3D model, just using a very big piece of drain pipe with a fan at one end blowing, and then putting some smoke and taper through and getting a flow. That can be that simple. But there are lots of hobbyists out there. But as with all things, please do run a risk assessment as a member of staff, and students, please get your teacher to run a risk assessment through if you are thinking, oh, that sounds an interesting idea.
I mean,
yes, Harrison.
So I was going to say it would be really interesting if I think students did that. So it's something that is still used in aerospace today. Is wind tunnel testing. It's something that we are developing, or running wind tunnel tests ourselves. If you do dive into it and you start looking at a lot of different fluid dynamics, models can be representative of large aircraft. Because essentially, as long as you scale everything down correctly, you can get out certain outputs and values. So it'd be really interesting if someone was to derive the drag coefficient from a 3D printed version of their model that they have in OpenVSP, and then compare the two, which is essentially what you do when we do simulation as well, is we compare simulation against reality. So that would be really interesting, actually. I don't know if you had any thoughts on that, Pablo.
Yeah, definitely. It's easier said than done. I think so. It's a very interesting thing to look into. Definitely.
You've got minimum requirements in terms of cost savings that we should be aiming for. Well, that's up to the students, and that's the idea. That it's for them to find those parameters and that sweet spot between making it commercially viable and not. And maybe they could then find a solution and then compare it to what is the cost at the moment for standard fueled aircraft and such like. And we did have one group last year, they started researching the idea of, well, if an area doesn't have an infrastructure for flights, and they looked at it's down in the Philippines area. The idea of island hoppers, maybe this, if they're going to have an infrastructure, maybe they should start with hydrogen fuel planes, because they haven't got one and it's a low impact in terms of the environmental impact. But it is really up to the students to come up with that answer. We don't know the answer. You can look back at posters from last year, and students could read those and say, well, that school managed to get that cost per mile, and that school got that one. We can probably enhance that. What is interesting, though, is don't automatically think just when you put your tank on and you put a cowling over it to reduce drag, it reduces drag. I tried and the drag got worse. And so it is a skill learning how to use some of this software. Hopefully that answers your question. We've got someone else, another one question.
Yeah, maybe while we're waiting.
If you're, yeah.
Oh, there's another question now. Fantastic.
Yeah, create 3D mode. What do you suggest research into materials and testing these? Perfectly valid for me. I think, testing materials and such like makes sense. And that's the interesting thing about our projects. Yes, you can take it off the shelf and follow it all the way through to the end. However, if you have a good idea and you want to, rather than this really talking to students, there's no problem with that. As long as when you're doing that, you are capturing what you're doing, you are approaching it in a scientific method, you are recording what's happening, and so that when you come to creating the poster at the end, the artifact, that reflects the journey you've been on. And sometimes you will go down a path and it will be a negative result. It didn't work. But that process is still very, very much very important as long as you capture it. And because, as I said, it doesn't work first time every time. So it is a it is a valid point to look at. And on that thing before, Pablo, I think you're going to contribute something. Just saying, for those with younger students, like year 9s and 10s, there is a requirement for a bit of resilience here for the students. It's very easy for them to just, I can't do this, but they can. It's just that little bit of support needed, and then they can move on. And the other problem some schools might have encountered is the software download, and that's why you've got it as a download off our site rather than going on the web and download it, which makes the IT departments very twitchy. We've got a version which you download, and that is relevant to the tutorials. However, some schools have still struggled, but the students themselves have taken it on themselves to actually run this on their own computers at home and such like. But then that's down to the individual students. So don't think you can't run it just because the school says no. And if you can't run the software, maybe looking into buying an airfix model and do the wind tunnel and do it that way and circumvent and still investigate fluid dynamics, still investigate those type of factors. Pablo, did you have something to say? I could have crossed you.
Yeah, I was just going to add in terms of the minimum requirement in terms of cost savings. Of course, the more the better. There's no minimum. What we do have, of course, internally, we have an understanding of what current aircraft are doing, and you'll find that is around 2.6 pence per mile. And right now, I think if you can get below 3 times that, or 2.5 times that, I think you're in a very good spot. So just as a nugget for you, I think that's a benchmark that we're putting there. But then again, as Mike said, this is something that you can always look into, and as Mike said, the more the better. And that's for the students to explore. Exactly.
I was going to say a secondary point, which makes it slightly more difficult as well, is we've got cost per passenger mile, but then we also have range. So that's another consideration, is how much, obviously, better range. You could have a really short range with a really low cost per passenger mile, or a really long range with a really high cost per passenger mile.
and bring that into, the model says flying between Edinburgh, Bristol and Edinburgh is what we're looking at ideally. But don't forget, there is a requirement for safety in terms of if you get to Edinburgh and you're circling above because there's a problem on the ground, you can't get down. You need to ensure that you have capacity. So don't think it is right. It's 500 miles whatever to Edinburgh, but I'm going to put 510 miles of fuel in my plane. You have to work in those factors, and that's an important part of the project is unpicking and research and realizing it is not just a very straightforward thing. There's a lot of factors that come to play, and as an engineer, you have to consider those. And one of the key ones, as we've been talking all the way through, is about cost benefits. Yeah, you can get a plane up to Edinburgh on hydrogen fuel. That's not the problem. The problem is making it financially viable rather than just 2 or 3 people. And if you start looking at the history of flight, research Concorde as an example of did the problem very quick to New York. However, it wasn't cost effective, and so therefore it's a technology that might be coming back into the fore if you look at current developments. So are there any other questions from the thing? If not, hopefully the webinar has helped. Hopefully it's given some direction. Thank you again to Pablo and Harrison for giving up your time and continuing to support the project. Hopefully this year, it builds on what was a very successful year last year. Final bit of chat going on up in a minute. And just saying here. So next steps for people who have submitted student registration forms, great. If you haven't submitted them yet, please do. And that, because once we know who is actually working the project, then we can direct resources if need be, if the opportunities come along, rather than constantly sending out blanket emails to the whole of all the Irish schools. So I think I'm finishing now. So thank you everyone, and have a good rest of the week. So I'll just shut this down.
Thank you.
Thank you all. Goodbye.